Okay, next in our Rube Goldberg series is elastic potential energy. And we're going to collect some data for two devices today. We're going to do a mousetrap and rubber band. So first, the mousetrap. Obviously, it's a spring-loaded system, and they actually do make excellent Rube Goldberg device triggers for different components. You can use the spring-loaded trap part here to set off the next component of your device. We need to know how much energy will be transferred, and we're going to keep this simple. We're just going to use the amount of potential energy loaded into the spring while we do work to set it. Okay? We're going to do work as we set this spring. And if you recall, the formula for work is force times distance. Okay, work equals force times distance. And since force and distance is going to be newtons times meters, you get Newton meters, and that equals joules of energy. So remember that, please. Okay. A little bit about Hooke's law, but we're going to kind of circumvent Hooke's law. And Hooke's law says that for a spring, the force necessary to pull back a spring is equal to a spring constant times the distance that you pull back the spring. Okay, so that makes sense. That means that and the reason it's negative is because the force of the spring is pulling in the opposite direction of the distance. So one of them has to be negative. So we throw that negative sign in there. Okay, so the spring constant for any spring can be determined by dividing the force by the distance that you pull it. Now, the potential energy of a spring can be determined from Hooke's law and the distance that you pull a spring. So knowing the spring constant and the distance you pull it, we end up with this formula. It should look kind of familiar, kind of like the kinetic energy equation. Now, if we substitute the equation on top into this equation here, we end up with 1/2 F over X, K equals F over X, times X squared. And if we simplify that, then we can cross off the squared and this X. We end up with 1/2 Fx, force times distance. Okay? Now this assumes, and we're going to see this in a second, this assumes that the curve for, let's change color here. The curve for a graph of force times distance is linear. Now it's going to be linear for a while, but as you pull a spring farther and farther, eventually it's going to flatten out, or actually no, it'll curve upward, because the distance, you eventually won't be able to stretch it at all as you stretch out the spring. So this only works for a short distance. And a quick note for you calculus folks, if this is force and this is distance, and we end up with a curve like this, we can actually, since force equals kx, using Hooke's law, we could make this kx. What this means is that for a continuously variable set of data like this, we need to find the area under this curve, right here. And that area is 1/2 kx squared, which you might recognize is the integral of kx with respect to x, if I'm saying that properly. Okay, back to the show. So if you think about it, as you pull back on this spring, it gets harder and harder to pull, so the force actually goes up. Okay? So what we really need is the average of all the forces from basically 0 up to some value here. Okay? And the way to get the average is simply to cut it in half. So you can just use 1/2 F times X, and that's what we're going to try to do. So I have the force sensor here, and let's see if it's a linear curve. I'm just going to graph the force as we pull on the spring. All right, I'm going to pull it back. going to start here. I'm just going to pull it, and I'm going to pull it at a perpendicular angle to the trap, like that. I'm going to go back down. Let's do a Command J here to spread it out. Okay, so, you know, from about here up to here, that's pretty linear. So I think we're okay with using the average as we go along. Now, as far as the distance is concerned, we can use our force sensor to get the force. In this case, the distance is actually a circular path. Okay, so what we need is the radius of this circle, and the total distance from here to here will be pi times the radius, because the whole circle would be 2 pi r. So this is 1 pi r right here. So let's collect some data. We'll start at basically 0, but I'm going to pull up on the spring slightly because this spring is not completely unloaded when it hits the wood. So there is a little bit of tension. So we're going to make 0 about here, and then we'll go about a quarter turn, 45 degrees, half, and then 3/4 of this arc. So actually that's going to be 1/8 of a circle, quarter of a circle, and 3/8 of a circle. Alright, there's our starting force. Okay, I'm holding it perpendicular. We're going to go about 45 degrees, right about there. Get something in the average there, ballpark. Alright, then we'll do the quarter circle here, 90 degrees. And then we'll do 3/8. That's about as far as I can go because the mousetrap itself gets in the way. So 3 data points should be fine. Give us enough data to use a mousetrap. What else do we need? Well, let's get the radius for you right here. So it looks like to the center of that spring, let's go with 4.3 centimeters or 0.043 meters. Okay, a quick summary of the mousetrap. You've got 3 values for the force. Those are going to go on the y-axis. Okay, and the distance, x, that we pulled, goes on the x-axis. Of course, it's x. All right. So the first value was 1/4 pi times the radius. Again, it's 2 pi r for the whole circle. And this was really just 1/8 of a circle. So 2 times 1/8 is 1/4. Then we went to a quarter of a circle. 2 times a quarter is a half. And then we went to 3/4. And 2 times, well, actually, sorry, 3/8. And that was 2 times 3/8 is 3/4. And you read the force off the screen, hopefully. If not, go back and get it. Now, the second one is for the rubber band. So let's do the same thing for a rubber band. Alright, I have a size 32 rubber band here. This is one of the newspaper rubber bands. So I figure they're pretty common. So if you got any of those lying around, that would be really handy. It's 1/8 inch thick by 3 inches long when you hold it like this. Okay? Alright, let's zero out the probe again. Alright, same thing applies here. So we're going to start at 0, which for our purposes here is, we're going to call that, actually, let's just call it 0. And I'll move the whole system over here. Okay, 0. Oop, there goes our ruler. Stay up there, there we go. And we'll do about 5. Yeah, we'll do 1 centimeter increments here. I can call them out for you in case you can't see the ruler. Still around 0. 1, 2, 3, 4, 5. Alright, just go back and pause the video if you didn't get those numbers. So once again, we're going to use 1/2 force times distance Fx. And I don't know if this will be linear, but you should be able to choose a distance that you pulled back on the rubber band. Get a force off of your graph. And once again, don't forget to multiply by a half, because it's the average across that distance. So for this assignment, 2 graphs to do a mousetrap graph and a rubber band graph, and I'll probably throw a couple of follow-up questions on the spreadsheet. I'll make a spreadsheet for everybody. It'll be right there in the assignment, and we'll talk to you soon.